All right, everyone, today I'll be going over like the basics of two things, autoencoders, and then a little variant to that called variational autoencoders, two really cool applications of a deep neural network. Quick spacebar. So quick note on like deep neural networks in general, if anyone is unfamiliar with like what they do or how they work, we can talk like forever about like, you know, the structure of them, how they work like, in depth, but I'll go over a general overview. You give it, I'm covering that. That right there is a representation of a deep neural network. You'll feed into it in that input layer, that x1, x2, x3, x4, your input, which can be basically anything that can be vectorized or put into a list. So you can think of it as like a picture that's split up into pixels. You can put each pixel in there, or you can put like features of a data set into there. Either one of those will work as inputs. And through a series of multiplications and like other functions applied to these inputs, you get outputs. So that sensor is just going to be a black box for now. If you know how it works, wonderful. It'll make some things a little easier to understand for the variational autoencoders, but you don't need to necessarily fully understand how this neural network works. Just know that, for example, right here, this like x1, right? The literal number that's going to be put in there is going to affect the numbers in each one of these, and each one of these is going to affect the numbers in each one of these. And what we're essentially making is a super like parameterized function, because at the end of the day, it's all multiplication and addition and a little bit of exponentiation depending on which activation function you use, which is just like before this number is going to be used to be applied to these nodes, you apply a function to it, so it's usually regularized between like 0 and 1 or negative 1 and 1. In essence, what you need to take away from this is you can take inputs and through learning through backpropagation, which is somewhat of an important word for this, you can take inputs and get outputs that can usually classify or tell you something about the input. And these neural networks are very powerful. They can do things like image detection, they can like classify handwritten digits, and this is the general structure of them. One thing to note is that like the input tensor or vector is a lot bigger than the output one. And if you click spacebar now, you can see that this is the structure for an autoencoder. So there's immediately a big difference that you can see is that the input and output layer have the exact same dimensions, which is important for how we're going to actually use this neural network, right? So this is a neural network that is characterized by, most of the time, equal input and output dimensions, a bottleneck layer which is smaller than the input and output dimensions, and it learns through self-supervision. So, and there's some terms here at the bottom, and I'll go over specifically, hopefully these two make sense, right? Equal input output dimensions, like these lines are the same length right there. So like you take input, you process it, and then we'll get into like what that output will be later, but just know it's gonna be the same size, right? So you take input, you like do stuff to it, and it'll be put out at the same size, right? That's one important part. Second important part is that when it gets transformed, it's not like one-to-one. It's going to get compressed at some point, which is a big important part of autoencoders. This is what's called the bottleneck, right? So just know that the center layer is going to be smaller than the input and output ones. And self-supervision, which is the next slide, just keep that word in mind. Oh wait, sorry. There's three terms here that I'll just define so I can use them throughout the presentation. Encoder is going to be basically this section, the part that takes the input and makes it smaller. Okay, so this is going to be the encoder right here. This is called the bottleneck, and that's pretty self-explanatory of a term, right? It's just the small part of the neural network that compresses the data. And this is going to be called the decoder. It's the part that takes the bottlenecked data and blows it back out into the output layer. So those are just terms that I'm going to be using. And now you can click the spacebar. So a quick thing on self-supervision is that if you've trained or worked with or like read about ML's uses in the world around, you'll notice that like most poorly performing or like biased ML models are biased because their input data is biased, which is a result of like the general idea of garbage in, garbage out. If you feed bad, improper, just like biased data to the network, it'll learn those biases as they are meant to and apply those biases to any tests that you have, which isn't good most of the time if you're like, trying to have something be a little more like holistic. And a large part of that is because it's hard to make labeled data, right? Like, because these neural networks need a lot of data to learn. And it's hard to, manually, especially for complex tasks, go and label every single one, like, oh, this picture is like tied to this patient's like diagnosis or whatever, and you have to like make sure it's in very specific terms. Data is usually spotty, you don't have a ton of it, that's super neat, it's a big problem. But one thing about self-supervision that's pretty neat is you don't actually necessarily need to label the data. Because in this case, for example, as you can see in that little autoencoder example on the right, the input is also the target. So you don't need this label that they're trying to get to. You don't need to say, oh, we're gonna input a picture of a 9 and the label needs to be, a representation of a 9 in some vector form. The input and the target of the network, what the network is trying to do with that input, is literally just the input itself. In this case, is what I'm talking about. That's called reconstruction. It's trying to compress and then reconstruct the data, right? So this is why it's like pretty cool or easy to make data and like push it through an autoencoder, is because you don't need to label it in a sense, right? So as you can read up there, self-supervised learning, machine learning process where the model trains itself to learn one part of the input from another part of the input. So if you consider like this block of data your input, you'll be able to train the model off of that and no labels. That's the idea of self-supervision. There's a little more like nuance to it than just input is the same as the output, but for this case, you can think of it as that. So if I move to the next slide. Here's an example of like self-supervision, but a little different. So you're going to take the input, which is the digit 7, and you're going to corrupt it. You're going to like mess with it to get that noised version of the image, right? And then you're going to feed that into the autoencoder, and then it's going to try and reconstruct the uncorrupted 7. So if you do this enough times with enough training data, which is quite easy to like make, right? You don't need to label these digits. You just need to write them and then apply an algorithm to add some random noise to them, right? And you can think about how easy it would be to like, well, digits is digits is quite easy to label, but you can think of like harder applications like images, for example. If an image is very complex and has a lot of parts in it, it's hard to label all that, right? Oh, a sunset with a palm tree, you don't want to have 100 people just writing that over and over again, putting these descriptions. But this is a denoiser autoencoder, for example. You can just take the image, add noise to it, make that the input, and make the unnoised image the output. And through training this model over and over again, what you can do is feed basically any image with noise into it, and it has learned to remove the noise from the image, which is, I think, pretty cool. And this is like a small scale example of that. As you can see, like it will reconstruct that 7 from this messed up 7. And it'll essentially, what the network or the autoencoder is learning is a representation, or like what it's going to, its job in this case, the application is removing noise from an image. That's one of the applications of autoencoders, which is pretty cool in my opinion, right? Like you want to remove noise from an image, this is like one of the ways to do that. So yeah, any questions about like this slide specifically? It is kind of hand wavy, and I'll explain why in a bit, because this is just an autoencoder. I want to talk about a variational autoencoder. Any questions about like how, not how it's doing it, but like how it's able to do that? None? All right, next slide. So, and then just back up to like the original image that I was showing you earlier. We're trying to predict the same thing as what we input into the model. So the reconstruction loss, or the loss for this model, which is essentially a measure of how well or not well it's doing, can be calculated in the case of mean squared error. X, which is the input, minus x prime, which is the output, squared. So if you think about that, right, if it's able to reconstruct it perfectly, and you do like a pixel-wise subtraction of those two vectors that represent the digit 4, it'll be 0. So the loss will be 0. And the further away from that original digit 4 that the reconstruction is, the higher that loss will be. And what do neural networks do? They try to minimize loss. So if you define this as a loss function, this autoencoder will, over time, through training examples, learn to reconstruct basically exactly the input after compressing it. So that's the goal of the autoencoder in this case. So why is that important? Well, it's actually maybe not that intuitive, but what's actually super cool about the autoencoder is what's going on over here. The idea of like the bottleneck. We're taking this high dimensional image. In the case of MNIST, it's like what, 784 dimensions, and compressing it into basically as little as we want. And we can blow that back up into the original image with some obviously slight messiness to it, but you're able to reconstruct, this neural network is able to make the digit 4 from something that looks like nothing like a 4, but holds the same information as that original pixel grid. So if you want to click the next slide. So this is an important concept, the idea of a latent space. If you go back for like 1 second, I forgot to mention, this bottleneck, like the vector or tensor that is stored within the bottleneck once the digit 4 is encoded, can be considered a point in latent space. And I'll explain like what that means later, but just think of it as like, say the bottleneck is 10-dimensional, that representation is going to be like a 10-dimensional vector, right? There'll be a point in that 10-dimensional space. And essentially what the autoencoder can do is you can say, hey, here's a point in 10-dimensional space. Can you reconstruct the digit that created that 10-dimensional vector? And it can do that for you if you give it that exact point. So next slide. So yeah, this is that right slide is like the main idea of why I think the latent space is so important. So autoencoders can take data from like high dimensions, right, 784, and compress it to really low dimensions, like 10 or so, right? And from this low dimensional data, which if you think about the idea of information, a lot of information has been lost. It's impossible to encode the same amount of information in 10 dimensions as it is 784. You just have more parameters to mess around with. Yes?
I think that's empirically true, but I don't think that's like theoretically true, because like if you have 784 dimensions, but like, you know, it's an MNIST picture, so like half of it's just black dots, you know. Like a lot of it's not important, or it can be represented, like you can represent a whole black row as like one feature.
Fair enough, for certain things, but the amount of expression you can make in 784 dimensions is always going to be more than what you can make in 10 dimensions. But you're right, so empirically true, but for this, like for example, like he just said, if you have a row of 10 black pixels, you can consider that like a 0, and you can blow that back up into as many dimensions as you want. But think about it as the idea that like information has been lost. The 4 as a visual representation doesn't exist anymore. You know, if you have like a 10 like pixels, and then they just have values in it that have been compressed by the encoder, you won't be able to tell that that's a 4. But the autoencoder can. It can tell that that like list of size 10 is a 4, and it can blow it back up into a 4. So what I'm trying to get at here is the representations created by the encoder, those points in latent space created by the encoder, are somewhat accurate but smushed representations of the input data. So if the autoencoder can blow up that bottleneck back into the input image, right? If it's actually able to do that, right? Then that point in latent space to that autoencoder is significant. It can actually work with that, right? So what I'm mainly trying to say here is that the autoencoder can make sense of those 10 dimensions. Like it can be like, oh, this point in 10 dimensions, yeah, that's a 4. And it knows that because it's been trained to know that or learn that. And I'll explain why that's really important, but just know that, yeah, what's up?
So what happens if you like look at a point in this space that doesn't correspond to something? Can it like, in this example, start making digits?
That's what I'm about to get to, right? But right now, for just a standard autoencoder, the points have to be discrete. Like
right. So like not every point.
Not every point, yeah. Not every point can. But for those discrete representations where it's been trained to learn that 4 goes to this, goes to 4 again, it can reconstruct the data. So one immediate application is dimensionality reduction. You can store the same information in like less dimensions, right? Say you compress it down to 2 dimensions, you can plot it, or 3 dimensions, you can plot it immediately. And not everyone here, I don't think, knows about PCA, but that's another dimensionality reduction algorithm. And an autoencoder can in most cases do better than PCA at like actually learning complex representations of high dimensional data and displaying it. So yeah. Oh yeah, what's up?
So when you give it like a 4, right? Is the goal for it to reproduce the exact same 4? Like, so for example, let's say I wrote a 4 with like a really pointy corner.
Yeah.
Right? Will the autoencoder create a similar 4 or like try to make like the pointy corner like same 4?
The goal is to recreate that same 4, but obviously, you know, neural networks, they can't predict like the exact same thing every time. The idea is they learn a general thing. So if you make the bottleneck small enough, everything's gonna look like a fuzzy 4, right? But the fact that it can recreate a fuzzy 4 is like an attestation to the fact that it understands what a 4 is, in a weird sense, right? So again, you're right, the goal is to recreate that pointy 4. It won't always reach that, but that's fine as long as it gives us something that looks like a 4, because then we know that it understands somewhat that point in latent space, and that corresponds to a 4. So, also like the size of the bottleneck does somewhat matter, because say for example, like, here's dog, bird, car, plane, right? They all have a ton of characteristics. Like this could be like furry, 4-leg, blah, 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 so on and so forth, right? And if we just put them on like one dimension, like the living axis, too much information is lost, right? Like, oh, what does it mean like for a plane to be a little more living than a car? Like, that doesn't really make intuitive sense. So, but if you choose your dimensions right, then you can get that grid on the right, which is actually useful, right? You can take these like very, very complex representations of like dog, bird, car, plane. You know, us as humans, we can understand that, but like for a machine to be able to kind of pick that out, pick those features out and put them on this axis, in my opinion, is quite impressive. Like the idea that it can tell that a bird is both living and flying, and a dog is living as well, but it doesn't fly. And that a plane can fly, but it's not living, and then a car is neither living nor flying. So, and what you can think about, if the bottleneck had a dimension of 2, right? Only 2 dimensions, that right there could be like a literal like points in that latent space, right? So like what you said, right? If I was to take this point, whatever it was, and if the autoencoder could generate this point and then blow it back up into a car, if I fed this to the decoder, it would tell me that's a car, right? So then if you go to the next slide. So, I guess that's what I just said, right? It can understand those points in n-dimensional space, in this case 2. So we've chosen our bottleneck size to be 2. But what if we selected a point somewhere else in latent space? So right there, right? So the point shown there, if this was to actually like be a representation and like the autoencoder understood the entirety of like the 2D plane, that should be like some kind of car plane hybrid, right? But what we really get in this case, and just to answer your question, for a standard autoencoder, if you gave it that point, you would basically get noise. Nothing useful whatsoever. And why exactly is that? So this is a lot of text, but I'll break it down and it should make a lot of sense. Standard autoencoders, like the one I showed you, are not motivated to encode items into the latent space in any fashion. They have no reason to actually get a representation or really understand that point because you never gave it data to do so or any motivation to learn what that point means, right? Like why would it just think of a car plane hybrid, right? You're not motivating it to. So as it says right there in a quote, autoencoder is solely trained to encode and decode with as few loss as possible, no matter how the latent space is organized. Like we said, we made a loss function, it's supposed to reconstruct something and that's its only job. This latent space idea to it, it doesn't even make sense. It's like, oh, I don't really care what that point is, you never told me to care about it. So that's what the autoencoder is thinking, so it's just gonna give you back noise, right? So, but obviously you can see how that'd be useful, right? If you train it on like a dog, bird, car, and plane, what if we did want to find out something that's like another thing that's living but flying, for example, right? So we pick like something near the bird, but that would also give us noise. And what if we want to like I said, generate a car plane hybrid? It'd be cool, right? Because obviously it understands like to some degree this is the characteristics of a car, characteristics of a plane, give us the characteristics of something in between, but it can't do that because it hasn't learned that point, right? So this is where like the meat of the presentation will come in. This is what a variational autoencoder can do to some degree. So what is a variational autoencoder? And I mean, you can just take a second to read that and absorb that description, and I'll explain how it correlates to the picture on the right. So the main thing to take away from that description is that the training of the autoencoder is regularized to avoid those very discrete, narrow spaces that we saw in the previous slide. With you can only select that point, and if you nudge it even a little bit, it'll give you useless noise, right? The idea is instead we get this kind of cloud, with like the center of it being those discrete representations. Like we trained out on a triangle, that's what a triangle is in latent space. But this is what a circle is in latent space. If you make something in between, it actually gives you something in between. This is the idea, that's what we want, right? We want them to kind of converge and get this like, we can pick anything from here. Oh, let's pick here, let's pick here, let's pick here. It'll give us something useful. And this is how it can be like generative, right? It wants to actually like enable generative processes. This right here, we never gave it that image, but it can generate it. If you take this point in latent space and pass it through the decoder, that's what we want to be able to do, right? So how do we actually go about getting the representation to look like this and not what we saw in the previous slide? So here's like the actual like intuition / math when it comes to these autoencoders, right? Or variational autoencoders. This is gonna be strange, I'm going to be honest. The person that thought of this, like, kudos to you, but like, it is strange. So instead of the bottleneck, as we talked about before, representing a single point in n-dimensional space, instead, the encoder network will predict a distribution, which is interesting. This ties into the 312, what we're doing right now. So the encoder network will give you, as you can see on the bottom, a vector of means and a vector of standard deviations, right? Which represent a distribution in n-dimensional space. And then you sample from that distribution, and that's now a point in latent space, right? You sample from a distribution over a space, you get a point, right? And then you pass that to the decoder. So removing the idea of n dimensions for now, just think about like, oh, hey, you know, if you have a standard Gaussian distribution, that itself is like, you know, oh, there's a X% chance you'll get this point, X% chance you'll get this point. You like take those chances, you pick a point, but now that's a discrete point, and you can actually feed that through the decoder, right? So that's what we want to change the encoder network to do. How much time do I have? Oh yeah, I got time. So yeah, notice how like that's the one of the big changes when it comes to variational autoencoders. So you want to actually start with like a distribution, and I'll have questions in a second because I know that's like one of the big parts of it. But one thing you might see is why isn't the standard deviation a mean? Why are they vectors? Why aren't they like points? You know, you can define a distribution with a variance and a mean, or a standard deviation and mean, but like what does it mean for it to be actually like a vector? Well, what that means is we are in n dimensions, right? You need to actually define, for example, this would be like a 3D distribution. Notice how we need something here and something here. Now take this intuition of like why we would need 2 means and 2 variances and blow that up into n dimensions, right? We would need n means and n variances to create a distribution over n dimensions, which we can then sample an n-dimensional point from. So that's why we need to generate vectors for means and vectors for standard deviations, right? So any questions on that? There has to be at least one.
So how does the sampling work? It just, the encoding, like, does it make a mean and standard deviation every time?
It'll take an input,
Yeah.
and it'll give you, like I said, a vector of means and a vector of standard deviations.
And then what does it do?
Sample from that.
So it just takes the most probable.
That's greedy. It could take something else. It could take something a little out of distribution, but it would do that like rarely. Just like, you know, it's like, oh, sample from a normal distribution. You're gonna get mostly the points in the middle, but you'll get some outliers.
So it
some
randomly samples.
Yeah, randomly
from that
samples.
probability. Okay.
Yeah, from that probability distribution.
Okay.
So yeah. That's it. Okay. Next slide.
Wait.
Mm-hmm. Mm-hmm.
Well, maybe you're gonna get to it, but I was gonna ask, like, how does backprop work?
That's a big part that I will get to.
Okay.
So yeah. So what we have done just now by adding the idea of a mean and a standard deviation to the encoder, right? That's what the encoder is giving us. What we've done is ensure essentially local continuity, right? Because now each input is turned into a probability distribution, there is no guarantee that the network will learn just one specific point, right? But instead, sometimes it'll be forced to recreate the original input from something that's a little out of distribution, right? So you can think of it as like one of those clouds. Notice how the clouds kind of stretch outward, right? If you want to go back a little bit, it's like, I think that one right there, right? So like you can think of this as like the range of, or like the possible samplings from a distribution generated by when you feed a triangle in, right? Oh, let's see. So like you feed a triangle in, right? And you get a distribution, and you sample from that distribution, and you'll usually get parts in the dark orange, you'll sometimes get parts in the light orange, and you'll basically never get points like way up here, right? Because there'll be a super low chance for that. But what's useful about that is essentially, if you sample a point like out here, for example, right, on the very edge, the network is like, okay, this should be a triangle. So it'll slowly learn like, okay, even stuff like here should be a triangle. But it'll be a little less of a triangle because I haven't seen it as much, right? So it'll stop it from just saying only this one point is a triangle and nothing else. It forces it to look outwards at things that are a little out of distribution. That's why we ensure local continuity, which is like what this is, by forcing it to generate mean and standard deviation vectors.
Do you get to choose where like the focus or the central points are? Or does
No,
it determine that?
not yet. Because it's just a distribution, that distribution could be
kind of
anywhere.
chooses how, say, like in this example, how spaced out a triangle and circle and square should be.
That's a very good question. With the framework I've described right now, you can't do that, but I'm about to add another part to it that lets you do that. So as of right now, technically no. I go back to the first slide. Yeah. Oh, sorry, no, where we were before. Yeah, right there, right? So it's local continuity. But like you just said, these representations could be all over the place, right? There's nothing stopping the network from just saying, okay, you want me to make distributions? All right, I'll make the variance super tiny and make the means incredibly distant from each other. And then what do you get? Discrete points, basically, right? Because if you have a distribution with super low variance, it'll always get the most probable one, and that'll basically be a discrete point, even if you sample from it. So you kind of need to force these distributions to actually be a little spread out, right? Because the network, it's easiest for the network just to like smush it together and say, okay, there, you wanted me to make a distribution? There you go. But it's a pretty shitty distribution. It's like 1 point, right? So that's what I'm saying right there. If you do not enforce the network to spread out its distribution through a regularization term, it'll hack the sampling to essentially make it discrete, which brings us back to square one by giving us very low standard deviation and very distant means. We can solve both these problems by modifying the loss function to force the network to expand its distribution a little bit. So if you go to the next slide. So a little note on loss functions. These deep neural networks we work with have no notion of right or wrong. We need to tell them like what is good behavior and what is bad behavior, what is rewarding and what is painful, and only then will we get the behavior we expect. Like you said, right? Like how do you know that they're going to be in that point? How do you know that they're going to be close to it? You don't until you force them to, right? There's one thing about neural networks, the loss function is what the network will optimize for, and if you don't tell it to optimize for something, very rarely will it actually give you that behavior back, right? And this is big for RL. One example I can pull up is, for example, in like a grid world search, right? You have an agent that's navigating through it. If you don't tell it that bumping into walls is painful, it'll probably go full velocity and slam into the wall in front of it, then turn left and slam into the wall next to it, and then go up and slam right. So you don't tell it like, oh, hey, you know, we're gonna put this code in a robot. The robot can't go 100 miles into a brick wall, so it'll demolish itself, right? But like the network's like, no, you told me to minimize for like speed. You want me to get the exit as fast as possible? I got the exit as fast as possible. It doesn't matter to me that I smashed into a bunch of walls. But if you add a term that's like, if you smash into a wall that's bad, that increases your loss, then it'll learn to not smash into the walls. That's why the loss function is so important. So we need to apply loss to the vectors generated by the encoder network. So that like bottleneck, right? We need to apply loss to that. We need to take that and say, hey, how well is this doing, right? So the intuition is to penalize the network for creating distributions that are far from the standard normal Gaussian, which is, if you remember, a mean of 0 and standard deviation of 1, right? So forcing the network to encode standard normal Gaussians, or saying, hey, you really need to make sure your distributions look like this one. It makes sure that all distributions will try to be in the same global space, so they'll all try to crowd around this center right here, right? Because you're forcing them to. Local spaces won't be incredibly discrete because the standard normal Gaussian has a little bit of spread to it. And blending can occur between multiple input embedding distributions, and this is a consequence of them being in the same global space. Because if you're saying, hey, variational autoencoder, your distributions, your mean and standard deviation vectors, need to look like the mean and standard deviation vectors for a standard normal Gaussian. It'll try to make it do that, but obviously, you know, all of those embeddings can't exist in one place. So you kind of get this like pushed together cloud, and that's when you get the mixing that we want, right? So by forcing it to be, you're trying to tell it, you go be that same thing, you go be that same thing, you go be that same thing, and they'll all try to, and they'll bump into one another and blend like we want them to. So yeah, and then the next slide. So there's one thing. So how do we check if a distribution is different from the standard normal or different from any other distribution? You use something called Kullback-Leibler divergence, or the KL divergence equation. I'm not going to say that full name again. KL divergence equation. It essentially finds how different two distributions are. Like for example, right, this one right here, the red is a standard normal Gaussian. This blue one is quite different, so it'll be penalized. The KL divergence between these two is going to be quite high. And the KL divergence between the yellow line and the red line is also going to be quite high. And you might say, oh, this one's closer to the peak, maybe it's not going to be as bad. No, but the mean is shifted. So its KL divergence is also going to be kind of high. So you can see like we're trying to get the distributions to be closer to this one, right? So this will be penalized, this distance will be penalized, this will be penalized, this will be penalized. That's what the KL divergence equation does. And now how do we use that in our loss function? So the old loss function was simply just input minus the reconstruction squared. But now we're doing the same thing, but we're adding in that KL divergence, and we're comparing the embedding vectors of mean and standard deviation to the standard normal Gaussian. So if the mean is 0 and the standard deviation is 1, and that's the distribution that the variational autoencoder encoded for us, this will be 0, or very close to 0. And the farther it gets, the greater this KL term will get. And what that'll do is increase the loss. So even if it's doing really well at reconstructing, it's forced to have the local and global continuity in the latent space because of this term. So that's why I was talking about why loss function is so important. Simply by adding this term to the loss function, we basically forced the network to behave in this interesting way that we wanted it to, right? So that's the importance of the KL divergence equation. And I'll give it like maybe 30 seconds on this slide so you can just like kind of read the, oh yeah, yes.
So you said that the means and the standard deviations are stored in like vectors, right?
Yeah.
Because you have n dimensions.
Mm-hmm.
So when you do this KL divergence formula, do you do it like for every dimension? Does that mean like if I have 10 dimensional vectors,
Yeah.
I plug in each pair and compare it to a 0, 1?
The way the comparison done is pretty interesting. There's a slide with the actual equation on there that you can see. It's interesting. You don't need to know exactly how the comparison is done because that's usually like a library of some kind. You have to know how it behaves when you give it inputs. So if you give it an input that's close to the standard normal in any dimensions, it'll give you a lower number. If you give things farther, like a really wacky distribution over here, and then the standard one, it'll give you a lower, it'll give you a higher score if they're different, yes. It'll give you a higher score if they're different. So yeah, but we will go over what the equation is, and you'll see it in a bit. So yeah, you can see the terms over here. I kind of built it up from the start. So that's why that KL term is important. Oh, sorry, both of you, yeah.
Wait, so, what if your data actually is like really far from the standard?
So that's the thing. Or standard autoencoders, right? What they will do is like because as you get into higher dimensions, data points are way more spread apart, right? 784 dimensions. These points are incredibly far in space. And for a standard autoencoder, that will carry over to the latent space in which they're embedded super discreetly and incredibly far apart. But now that we're working with a distribution, and we're trying to force that distribution to be closer to like the standard normal, they will, like, if you think about it, right, if the network tries to do that, tries to get something super far out because its 784 dimensional input was super far out, this term is going to be incredibly high. And it'll tell the network that's bad. And then through backprop, it'll learn to like descend to where this is going to be lower. And that would include, in that descent, optimizing for this to be closer to 0, 1.
Okay, sure. But I guess I'm a little bit confused, like why we're trying to get them close to the normal distribution, like the standard Gaussian distribution in the first place, because like, okay, what if you're feeding your autoencoder, like for whatever reason, you want it to learn how to reconstruct like the endest 4-digit and then also pictures of cats. Like they're far apart and they probably should be. Like you probably don't want to interpolate between those things. But I guess like nobody does that. Maybe that's why we can just do this.
You would get nonsense in that case in the parts in between, because like if you can't concretely think of something that could exist in between those two,
then you don't want to do that.
Yeah, exactly. You don't want to do that, right?
Yeah, okay.
So you usually try to encode stuff that's closer in like actual understanding, right? Like the same type of thing. You can get something that's actually useful in between. So you have a question?
Yeah, so I know that you already talked about this, but why do we use the mean and the standard deviation as vectors, and should I think about that any differently than I would as if they weren't vectors?
So the reason they're vectors is because if you have a standard 2D Gaussian distribution, right? You have one standard deviation and one mean. How would you, with only one standard deviation and one mean, blow that up to 3 dimensions? You can't. You have to replicate it, right? You have to like say, oh, okay, so like the mean for this axis is going to be 0, and this variance for this axis is going to be 1. And then you make another axis, and then you give it, another mean and another variance, and those two together make that little like bump plot that I showed earlier. In that intuition, the idea that you need another mean and variance for every dimension you increase is why, for an n-dimensional bottleneck, we have an n-dimensional mean vector and an n-dimensional variance vector.
Okay.
Because, to create an n-dimensional distribution, you need n means and n standard deviations.
Okay, that makes sense.
Next slide. So, I'm not done yet. Yeah. Next slide. So this is the part that Chase was talking about. I do want to get to other stuff, so we'll go back to it. But this is how we're able to backprop through through that that sampling, right? Because usually that's not backpropagatable. I'll say this really quickly. If you don't understand, that's fine. This is mainly to answer Chayton's question. What you do essentially is make it, hey, instead of getting a distribution, let's just say we're trying to predict or optimize this function, right? And you're gonna have this term, which is some sigma term, and this mean, which are both numbers that you're trying to get or use. That'll be in the vector. And you'll have this constant stochastic term, which is the normal distribution. And you can, if you multiply these together, you get a point that is like if you sample from that distribution. We'll come back to the video afterwards because he explains it really well, but essentially know that what you do is when you're training the model and stuff, to make it back propagatable, you're really trying to get the z equals sigma sub x times whatever the hell that symbol is, plus mu sub x. If you read on the bottom, that might make a little more sense, Shane. But again, I want to get back to this after I'm done with the rest of it, and then it should hopefully make a little more sense. So we'll come back to it. So here's the Kullback-Leib KL divergence equation. So I gave one for a discrete probability distribution function and one for a continuous one, and P and Q in that case would just be the distributions, right? How they come up with that, I don't know. The code example to me made more sense, and it was more concrete. So you have a question?
No.
Oh, okay. So you can just take a second to absorb that. Hopefully is something in here answer your question, Amanda? No. again, it's one of those things that you use and you understand what it does, but how it does it is some mathematician wrote a paper about it before. Yeah. So yeah, that's what the KL divergence is. Like actually, if you wanted to know how to do it, if you look at the code itself, it's actually not that bad. It's like one line. But the integral makes it scary over on the continuous PDF side. So, yeah. So now, like, what am I trying to get at here? Why are variational autoencoders so cool to me, right? So let's go over what they both can do. They can encode data into latent space. The standard one does it immediately as a consequence of its architecture. The variational one does it through this little trick, to the sampling trick, right? You can, in the standard and variational one, you can reconstruct a discrete latent space points back into input tensor. So even though we're encoding these distributions, the ability of a variational autoencoder to take a discrete point and turn it back into its like blown up form is still there. Now, this is where the standard autoencoder kind of falls off, right? Or actually, one small thing, standard autoencoders can denoise better like right out of the box, and variational ones can denoise a little bit of architectural modifications, or that's not really what they're meant for, but that's like just one application, right? Standard ones are more lightweight, and like I guess easier to understand, which is useful for people that are just getting into ML. But standard autoencoders simply can't reconstruct like proximal nearby points in latent space. They just fail, like I said, right? It can't make that car plane hybrid because it was never told to make or understand what a car plane hybrid is, right? And it can't act as a generator. Meanwhile, variational autoencoders, if you give it this point in latent space that it hasn't seen before, it'll generate something new for you that won't just be noise. So, and next slide, I think, like this one. Here's an application or use for these things, right? You encode these emojis into latent space and you pick a point between them and you get a combination of the two. That's an example of a use of a variational autoencoder, for example, right? Another one, denoising, dimensionality reduction, like I mentioned earlier. This is a consequence of the fact that they have a bottleneck. Through dimensionality reduction, you can do clustering or classification on that reduced dimension data. Smash together two things to make a new thing. You can do feature detection and you can do anomaly detection. Can you think of any other cool uses for like this idea of melding together two things and popping out a new one? So, say something.
One cool application is you can take someone. I think I said this.
Yeah, the mustache one. Yeah.
Yeah, you can take a picture of someone like holding a fake, or someone with a mustache, say, and then get the latent vector representation, and then get the picture of the exact same person, same angle, same everything, but just without the mustache. However, you can shave, I don't know, whatever, and then encode that vector, and then subtract the difference between the two vectors, and that's your mustache vector. And so add it to anyone who doesn't have a mustache, and we'll give them a mustache when you decode it. Subtract it from people who have a mustache, and it'll remove the mustache when you decode it.
Yeah.
Assuming you train it on sufficient data.
That's why it's cool because like
Does that work on a regular autoencoder, or does it need to be variational?
It needs to be variational because we're doing interpolation between the
yeah.
splits. Yeah.
Okay, wait, so I have a question about that. I feel like regular autoencoders can interpolate, just maybe not as well.
Because you're not really interpolating, you're just changing the. Oh wait, no, you are. Yeah.
You're sort of traversing the latent space in certain ways, but like, so actually, like, I did try this with like MNIST on autoencoders. Like, it works within the very local spaces. Like, it's very discrete.
Because it's like, I mean, yeah. So I guess they tend to overfit the latent space to like the classes, but it's like Cholet's manifold hypothesis thing. He would argue that literally every neural network must be approximated with a manifold. Anyway, so then it doesn't. But yeah, so maybe you could use this for like.
I see creative applications for like businesses, like say you're a shoe company, you want a new shoe, take two of your old ones, put a dot in the middle, and then you got a new shoe.
It'd have to be very, that's like,
Something like
you know,
that.
something with like, machine learning is getting super powerful nowadays, so low key maybe, but like, yeah, you have to think about, there's so many dimensions and features, and just set up your input like somewhat, like maybe like the color of the shoe, like you can totally do it with like shoe colors, right? Like, put the same blue shoe and the same red shoe, you got like a purple shoe, right? Like that totally work, but yeah. that's like one application, generation for sure. Actually, Andre, question. Is there variational autoencoders for some like architectural like build on top of them a little bit? Are they state of the art for generation, or would that be like a GAN or something?
Yes, so actually, do you guys know about, what is it, Dolly? Well, yeah, everyone, Dolly. Dolly uses a variation of variational autoencoders called vector quantized variational autoencoders. And the idea is that like you have the latent space, and okay, these ones are continuous, right? So, but it's like the latent space is still really big. And so when I want to sample something, I'm still really specific. I'm like, I want this point in the latent space to be decoded. But if you think about the way that creativity functions, it actually functions from less information than more information. You know, if I'm an artist and you give me a very detailed representation of what you want me to draw, I'm not going to be very creative. If you give me something vague, I have direction to move. And so the idea of vector quantized variational autoencoders is that you have a discretized latent space, which the math is kind of complicated, but then like you force the encoder to do even more work and almost speak in like a language, like in discrete symbols. And then the decoder picks that up, but it follows a similar logic. That's what is used to do like Dolly type stuff.
So it's really powerful. Okay, there's another question, then I'll get to you. Yeah.
I kind of forgot it.
Oh, sorry, man. So
I was just gonna add to that, the alternative is like, if you've seen Stable Diffusion, that it generates like really high resolution images, and it's a diffusion model. I don't know if you guys know what that is, but they use a lot of the same concepts as autoencoders, where they, particularly the variational ones, where they learn the parameters that describe a distribution, so, and then they denoise images, and they just iteratively denoise until the image is like really high definition, and so that's kind of cool.
you should do a journal club on
I did remember. Would software that like remove shadows or like maybe remove an object out of a picture use something like this?
If it was convolutional, maybe, yeah. Because, you know, a standard, well, actually that's a tangent.
But can this do that?
It can, if it's like if you can kind of point it out in the picture, you can probably remove it, right?
Okay.
If it's like an idea, maybe not, right? Like, remove, you know what I mean?
But if you like circle, I want this removed.
Possibly. That might be something else. Again, they're not like throwing this everywhere, but.
Yeah.
And wait, can you get the next slide? I think I have one more thing. Yeah. Just some more applications. I think my favorite was this one. I actually laughed really hard when I saw that one.
I think they just draw these.
They probably
I don't
draw
think they
these.
generate
Yeah.
this.
Do you have the files for these?
He can make them on the fly. It's kind of crazy.
Basically, my phone keyboard can take 2 emojis and then it'll make. Not every emoji can do this, but like the bacteria one can take almost any face emoji, so you can get like smiling bacteria, sad bacteria, crying bacteria.
If you save the files, I can add them to Discord.
Oh,
I like that one with the.
This is on a website. Just look it up. Like Google's combined emojis.
I like the double skull. Yeah, that was good.
I think one of my favorites is just combining it with like monkey faces, so then you can get like the crying monkey or like the laugh.
Space.
Google keyboard. You can
it's
just
Google.
download that and do it yourself as well. It doesn't have to be an Android phone.
So no need to play these because we definitely don't have time.
Like,
But-
it's the place to keep them.
Yeah, I will
It's on
talk.
Google.
I'll talk quickly about the thing on the right, like 1 second, and I'll call it a day. Basically, what you can do with disentangled variational autoencoders, which is like a variation on a variational autoencoder, you can force those like every single like element of the latent space, like the 0th index, 1st index, 2nd. You can force them to actually like represent something tangible. Like if you're doing this with faces, the first like index would be the eye color. The second one would be the hair length. The third one would be like the face shape or the nose shape. It can learn to actually like really like discretize these different things. Like if you increase this number, it will make their hair longer. How it does that, it's in that video, it's pretty cool, but just know that that's possible. You can make some really cool things with autoencoders, which at the end of the day, like really all they do is they just compress and like decompress, right? And you can get all this crazy behavior from it. So that's why I think these are super, super cool. I want to personally throw them into a project of some kind. They definitely have creative applications, like you guys have said, but they definitely have like clustering, dimensionality reduction. Probably just throw them in a lot of things and it could lead to some pretty cool behavior. So yeah, that's really all I had for Journal Club today. One click space, there's like a little thank you slide. Oh wait, no, resources. This is basically, this right here has 90% of the information I talked about. So if anything was confusing, read this. It's wonderful, wonderful article. It's so good. And then the videos, that were linked as well. And the last one, yeah. Thank you. Any questions or discussion? We can just kind of chill and talk. There's not much. Oh, you want to stop the video, by the way?
Oh yeah.
Pass the video.
Square button.